All right, all right. So thank you. Sorry again. I know that listening to the crazy Spaniard is not the best thing, but someone put some excuse and couldn't come, so I'm here to support and entertain you more. So Rodrigo asked me to do a talk, and I couldn't figure out like what to talk about, so I decided to talk about everything. But I think it's going to be cool. So I'm going to mainly talk about a tool that I developed apart from CPython. It's called Memray. So what Memray allows you is a tool that allows you to measure the memory usage on your programs. So this will allow you to have, like, if you have a Python program that maybe is using like Django or whatever, but if you have like some ML applications or you're using scientific things or whatever it is, this tool will allow you to know why your program is using too much memory, or even if it's not using too much memory, like why is using the memory is using, right? So it's a debugger tool that will allow you to identify what's going on. So the first thing here is like to know why is this important? Because like the standard library comes with a tool called tracemalloc. So it's a module that you can use. Probably nobody uses it. I'm also co-author of that thing, so it's a bit weird that I'm telling you not to use it. But so for instance, I think I have an example here. Right. So this is how you normally will use the tracemalloc module. You basically import tracemalloc, and then you call tracemalloc starts. You do some stuff here. We're using this thing here, and then you say tracemalloc take a snapshot, and this will take a snapshot of like what you're using at the time in memory, and you will be able to print like the top 5 allocations. All right, that's kind of good and all, and it's useful, and that's why we added it to the standard library. This is not a third-party module. It's something that goes in the standard library. But there is a problem. The problem is that normally tracemalloc allows you to know Python objects, but here I'm doing something a bit funky. I'm using memmap. If you recognize, this is the system call that normally malloc itself uses underneath, and this goes to the kernel and asks for a bunch of memory. Here I'm asking for a lot of memory. I think it's like 100 megabytes of it. But if you run Python over this thing, you will see that tracemalloc thinks that you only allocate 96 bytes. Yeah, no bueno. The reason is because like tracemalloc cannot see C allocations, right? And memmap is one of these low-level C allocations. And you will say, well, but Pablo, like we don't program in C, we program in Python. Yeah, well, surprise. What the C Python in what is the C in C Python? There is that, and also the fact that like at the end, like even if you program in Python, most of your things that you run normally run compiled code underneath, because otherwise will be stupidly slow, right? Like I hope that I'm not breaking your heart with this, but with you call your LLM whatever, like you're running a lot of compiled code that probably C++ or Fortran in some cases. So like think it twice when you are saying that you're a Python developer. So yeah, that is kind of bad, right? So I created this other tool that is not in the standard libraries. It's outside. It's called Memray. So you need to pip install Memray, and it will allow you to like actually understand a bit better your program. So I'm going to just basically show you a bit how to use it and like how to read the output, because it turns out that like all these debugger tools, so an output that you have never seen is quite confusing. So like it helps a lot that someone kind of explains to you what you're saying. So we are going to see a bunch of those. Before the end, I have something interesting. So I'm going to show you a bunch of tests. I think I have something here. Well, anyway, so one thing that I wanted to show you first. So testing.py. Okay. So imagine that you have a test. Who here uses PyTest? Okay, so mostly everyone. Okay. Don't you find a bit weird that if you say test the thing, right, and like maybe it's a test and then x equal 1 and y equal 2, and then you say, I don't know, assert x plus y equals 4. Right, okay, maybe I should revisit my math studies here, right? But like, it's a test. So okay, so there is this thing, and when you run PyTest over it, so Python is PyTest testing. Don't you find this weird? Like, PyTest is kind of useful, but look at this. Like, it basically tells you what the hell is going on here. If you create a more complicated expression here, like for instance, you say, okay, I'm going to just, I don't know, divide by x and like plus 1 or something like that, right? So if you run it again, it look like it's kind of able to reconstruct the instruction and put it there. You may never think of that as weird, but it's really weird because like Python has never seen the intermediate values, right? But still PyTest is able to do it. Does anyone here knows how PyTest does this? Yeah, magic. But we are here to see the magic, right? Like we don't like magicians. Okay, so I'm going to show you how PyTest does this, and you're going to feel horrified. So this is the lie, right? So when you run this test, you say, "Oh, how beautiful test! You know, like fantastic, exquisite. I should be promoted because of this quality." Uh, and then you see, like, of course, it's super simple, right? Like, it's just asserting a bunch of stuff, but it's assert, right? Like, and that's what you like about PyTest, because if you have ever used the unit test model in the standard library, which only core developers use, because like we are forced to use our own stuff because we cannot install PyTest. But if you ever use this, it's kind of annoying, because instead of this assert, you will need to write something like, self.assert equal, and then you like pass this thing, and you cannot use the equal. You need to put like this. So it's disgusting, right? Like, not great. But this is so clean, right? Assert. So I'm going to show you like what really happens here, which is not fantastic. So first thing, we are going to have our cool testing, which is here. So I'm going to just copy this little assert over here. Actually, let's copy just the entire thing. All right. So we are going to start this, and we are going to say, well, we have some code here, which is going to be our test over here, and let's see what happens. So PyTest has this secret underscore PyTest thing, assert right. So assert, no, yeah, asserts maybe. No, okay, 1 second. This is the problem with like live calling. So import PyTest. Where is this guy? Okay, so this is in this place. So this is what you are not supposed to do. You're not supposed to look at what is going on here, but I'm going to do it. It's called assert underscore or something. Assert. Assertion. Oh, assertion. Oh, excuse me. Okay. Okay, assertion. We are very important. Assertion. Right? Okay. Now we're good. Okay, so now I need to recover. You see, like, that's why having the other thing is good. Testing. Okay. One. Okay. No, I think it's fine. No. For the online streaming. Yeah, all good. O melhor palestra do mundo. All right. Okay, well said. I'm going to continue, right? Or do you prefer to see how many engineers are needed to fix everything? No, the other one. Uh, good. All right. All right. Yeah. Sorry. Yeah. Well, anyway, it's the C++ people. They don't want you to know. The PyTest developers. All right. Anyway, so we were here, and then we have our test. So it turns out that PyTest really doesn't just grab your code and runs it. It does a bunch of evil stuff with it. In particular, what it does is that you have this code here, right? So the test. And what it does is that first it uses the Python AST module to transform this thing into like the internal representation that Python uses. You can actually dump this using the AST dump function, and you will see that it's like kind of like a lot of structures, right? Like it's structures representing the code that you have there. So we are going to grab this guy, and we are going to call it tree, because it's a tree. And then PyTest does this thing called rewrite asserts, and then we pass the tree here. Sorry, I need the source of code. And it does something to the tree. But the problem is that if I do tree, you don't see anything. So you say, well, what about if I do ast.dump tree? And okay, so now this is bigger, but like you still cannot see anything. But thankfully, we are nice people, and in the core developer thing, we added recently this ast.unparse function that does the opposite. It just goes from the stupid tree to the source. So if I print the tree again, you're going to be horrified about what PyTest really is running for your code. It's this thing. Oh no! So this is the actual code that PyTest runs when you run the test, and you will see a bunch of weird stuff apart from me, right? So one of the things that you will see here is all these weird variables. Like I'm risking it by going close to that thing, so I'm going to put my stuff here. So all these weird variables with the at. So the reason it needs to do all these weird variables is because it needs to capture the temporary variables. Like when you add 1 plus 1, it wants to capture that was 2, but then you added 1 to it and now it's 3. But to display the error, it needs to say, well, you added 1 plus 1 and that was 2, and then you added 1 that is 3. So to display the 2, it needs to capture that somehow. So it has this like intermediary weird shit. Like you can see all the operations like the addition first, and then the division, and then the equal. So it captures everything in the individual one, but it needs to store it somewhere. And the problem is that to store it, you need variables. But because this is your test now, if you have a variable called temporary value, it may override your temporary value. So it creates these illegal variables called add PyAssert. So you cannot create that because that's a syntax error. But if you modify the AST, you can. So PyTest does it. And like now you have all this like disgusting thing. And like at the end, if the last check, like this PySet assert 8, which is the equal, fails, then it prints all this code, which is the thing that formats your code now there, right? And now you have this nice code over there, and then you're happy, and then you can be promoted once you fix your test that you fail. But this is what is going on. This is the price of simplicity, right? Not fantastic. But you will see, well, that's kind of a neat trick. What is this like by assert thing? Like, it's kind of weird that you use these illegal names. So a question that you may ask immediately is like, who else is using illegal names? Only the PyTest people? No, it turns out that you all are using illegal names. Do you know where? Yeah, it's Python, obviously. I mean, I am using illegal names, not you, but like, Michael runs in your computer. So. But like, do you know other, like, who knows another illegal name? Come on, like some proud people. Okay, I will show you the secret. But once you know the secret, you need to store the secret and like hold it and not tell it to other people. So if you think about it, when you write the list comprehension, so for instance, you do x squared for x in range 10. So in Python 2, this used to, like if you, for instance, have a variable called x here, that it was like none, and then you run the list comprehension, x is not modified, x still is none outside. In Python 2, this was not the case. In Python 2, it used to be that, I don't even know if I have Python 2 here, but you can believe me. It used to be that the none now is not none, is 2, right? That was leaking scope, and that was kind of weird. If you think about it, it's kind of weird that you do this list comprehension and now your outer scope changes. So we added this like weird thing. So this list comprehension doesn't leak the scope. This means that when you assign to x inside the list comprehension, it's not seen outside. But that's kind of weird because the only thing that does this in Python is functions. But this is not a function, or is it? Turns out that this is a function and you don't know it. And you will say, well, if it's a function, like if you have a function, for instance, like f, right? And then you say, well, I have a bunch of local variables here, like I don't know, y and x. You can totally call this thing called locals. And if you do locals, f, it will show you like all the local variables as a dictionary. It's kind of neat, right? Like you can see that x is 4 and y is 3, and then you just change it, it changes, right? So if the list comprehension is a function, you're supposed to use locals here, and then you can see the local variables. So let's do that. Let's see what happens. Oh wow! Okay, a bunch of things. So let me let me change that. Let me start again. Okay. So what is going on? Okay. So all of these are the local variables, but look at this guy over. Where is this? Dot 0. 1 second. I'm trying to fetch it. Okay. 1 second. This has been. Let me do it over here, just so we don't have the spillage. All right, so let me do it here. Sorry for the black background, but locals for x in range 5. All right, so look at this. This dot 0. So this thing is the thing that holds to your iterator, because like when you do in range 5, nothing is assigned to range 5. So Python thinks, nobody is using range 5, I'm going to kill it. So we need to put it somewhere. But obviously we cannot use any name because like in your list comprehension, you may use temporary range or whatever. So we also use this dot 0 secret thing. Like you cannot do, right? Like if you do dot 0, it's going to tell you like, no, but we can. All right, enough horrendous, horrible thing for today. Okay, so memory, what is this memory thing? Okay, so memory is a memory profiler. So the way this works is that you have for instance, let's pick this memmap stuff, and like, instead of like running this trace malloc thing, let's remove all the trace malloc stuff. So no more trace malloc. So now we are We are using this mem map, and we are requiring here 100 megabytes. It's a lot of memory. So the way this works is that you call memory run, and then you pass your Python script. And then memory will run and will generate this file. And with this file, you can do a bunch of stuff. The more easy things that you can do here is to basically say what the tool tells you to do, like a robot, So you just do it, and it generates this like nice HTML file. And because I'm in a Docker container, because macOS sucks, so I'm going to just copy this outside and like run it here, open blah, blah, blah. All right, so can I open this thing, please? Okay, nice. Okay, so now it opens this nice page, which now is very simple because the sample is very stupid. But you can see now that, okay, if I hover here, it says that, oh, this allocates 100 megabytes. Nice. It turns out that this code is very simple, so you can see that not only is telling you that you have allocated 100 megabytes, it also tells you who called this function, in particular main, right? Because there's nothing above. Obviously, this is very simple, but let's look at a more complicated example and let's see how to read these guys. Because if you learn how to read flame graphs, which is what I'm showing you here, you're going to be very powerful because a lot of profilers and debuggers use this output. And at the beginning can be a bit annoying. So I do have here this example, DB example. So this is a more complicated example. This creates like a SQLite database in memory. It does a bunch of weird stuff just so it's worse. And it just creates a bunch of queries. So nothing super wrong, it's just a bunch of queries against some fake data. But let's run it. So you run memory run, and now you run over DB example, and it's going to produce another one of these bin files. And then you just run this thing again. We will see other things that you can run, but right now it's just this. Hopefully I can just open this over here. Voila. Okay, so now it looks a bit more complicated. I'm going to make it bigger for you. So first thing, now that we have done a bunch more, we have this plot over here, which shows you how memory is growing as the program is running. Obviously, it didn't take a lot, but you can see 2 lines. Okay, but this is interesting. There is 2 lines. One of them is this residence size, and then the other is the heap size. Who knows the difference? They are different, yes. But yes. So residence size is physical RAM, and heap size is what you ask for. So it turns out that if you can ask in Linux, at least on POSIX in general, I don't know what Windows does, but nobody cares. So you can ask for like a gigabyte of memory, and the kernel will tell you, of course, here is 1 gigabyte of memory. I totally have 1 gigabyte of memory. I'm not lying about it. But it turns out that it gives you nothing. Only when you use that gigabyte of memory, then the kernel will say, oh, actually, here it is, right? And the difference between the two is this. And you can see here a bunch of interesting things. It works the other way around. For instance, here, if I zoom by the power of JavaScript, okay, wow, amazing. Okay, so you can see here that the orange line, which is the heap size, goes up and then down. What this means is that I requested more memory, so I requested 77 megabytes of memory, and then I just didn't need it anymore, and I free it. But the residence size, which is what actually is sitting in RAM, stays the same. This is the other lie, because when you say, Mr. Kernel, I don't need the memory anymore, the kernel says, whatever, man, I'm not doing anything. It turns out that memory is quite annoying. That's the reason you need tools like this, because sometimes you go and say, Jesus, my Python application is using 2 gigabytes of memory, and I throw my LLM bullshit. Why is it still using it? Well, because even if Python says that it doesn't need it, the kernel says, whatever, man, you stick to it. And now this at least tells you what's going on. Fixing it is a different problem. But at least it tells you what's going on. All right, so the plot is interesting, and now we have these two. We are going to see this effect in a second. Okay, but now we have this thing. And this thing has historically been really complicated to read, and people find it confusing. So let me try to explain it. I'm going to try to go close to this. Hopefully it doesn't explode. Oof. All right, so what you're seeing here is the tree of calls, right? So every individual path from the root to one of these leaves is a different possible path that your code took. For instance, if I click here, I can just zoom it here, and you can see one stack. Imagine you're in this function, and you ask who is calling me, and then who is calling me, and then who is calling me. So in this case, this function called choices is being called by this function called random string, that in turn is called by this function called setupdb, etc., etc., etc. So this is one possible call. And then we have this other possible call over here, and we see again that this function setupdb is being called by main, etc., etc. And what we do now is that we join all those calls together. And because some of these callers have the same callees have the same caller, then they form a tree, right? when you say tree in a public talk, people just run away because like it's like, oh, stack's okay and string's nice, but tree, man, like that's scary. Anyway, but this is a tree and it's not that bad. And then the other important thing when you read this is that the bigger the bar is, the more memory is being allocated there. So for example, like if this one over here is very small, so like very small amount of memory, like 3 megabytes is being allocated here. But if I hover over this, you can see that this is 41 megabytes. So very easy, right? When you are reading these things, what you are searching is for big bars that are sitting down there. And I said, like, and you want the bottom ones because the bottom ones are the ones when the thing happens. The one above, for instance, this one is the caller. So that helps you to know how it happened, like who called the function that is allocated memory. But like the one that you're searching for is the one down here. And this is very important. So for instance, let's see more complicated examples. So we have in the documentation, we have a bunch of them that are quite cool. The logo is very cool. Like a dragon snake, it's a snagon. Okay, what is this thing? Examples. Examples. All right. So this is very cool. This is a SQLite application, and this will show you something cooler than memory does. So this is a more complicated one. So for instance, in this case, a lot of things were here allocated, but this shows you another superpower of memory, which is that you can see that now there is two colors. There is this yellow color, and then there is this green color. And turns out that what happened here is that I'm using SQLite 3, but the green frames here, like these bars, are Python code. So here you can see values, extend something, something. But then you see that this thing is calling yellow frames that have these weird names. And when something has weird names, it's probably C or Fortran. In this case, it's C, because SQLite is in turn written in C. And this is quite important because if you just say that there is 27 megabytes allocated in values.extend, generate values count, you say, oh, okay, thank you very much, but what the hell is going on there? But then you say, well, I need to know what is happening underneath in the C code. And if you have a good breakfast that day and you can look at C code without like getting nauseous, you can actually like ask memory and it will show you not only the Python code, it will show you the C code. So for instance, on the other part of the flanker over here, you have this connection execute many insert statements, which is the last Python frame. So if I told you that this line is executing 10 megabytes of memory, you will say, yes, by why? But now that memory allows you to see C code, you can actually see the bottom of the iceberg, which is this insanity going on here. But if you have done any database courses in your university, you will see this B3 get page, blah, 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 blah. So this is the B3 that is represented by the database rebalancing itself. This is very interesting because it means that those 10 megabytes is not because you ask for it in your query, it's because it just happens that when you were doing your query, the B3 needed to rebalance, which is an operation that it needs to do from time to time, and that allocated memory. So you can tell your boss that it was not your fault, it's the B3's fault. Then you will need to explain what a B3 is, which is a different problem, but sounds very heavy metal. So like probably they say, oh, this person is very smart. More money. Okay. And this is very important. For instance, another example that you have here is you are into science. We learned a lot about science this morning, right? So maybe you shouldn't be into science. But like another thing that you have here is this embody thing. So this is an embody simulation. Christian is not here. Where is Christian? No, Christian. Okay. Christian used to do this in his PhD. So here you can see a bunch of interesting things. This is using NumPy. And if you look at it, there is some very interesting thing. Importing NumPy takes 63 megabytes of memory just by importing. So when you run your scientific application and says like I'm not using memory, why I'm using 63 megabytes of memory? Well, it turns out that science sucks. So because like just importing takes 63 megabytes of memory. You can actually see like who is the culprit if you go down. Is this core multi-array UMath import? No bueno. But if you go down, there is a bunch of things here. Like in particular, you can see that, okay, there is this DL open check. And at the end, what is this pthread create? Oh, NumPy, just by importing NumPy, you are creating threads. Disgusting. All right. But then you can say, I don't care about this. There is this magic checkbox you can check, and it will hide all these bananas thing. Oh, much simpler. No more NumPy madness. So now you can like simplify on your code. And here you can see that I have this scientific mega function called add, which is adding stuff. And you can see that add, because this is called NumPy, is calling these things underneath. And you can see all this like FFI, whatever. And at the end, like, it just shows you that it's adding particle speeds. So you are using like big scientific simulations and you wonder why it's using so much memory. And this happens because when you submit in these mega clusters, they probably will ask you to reduce the memory usage so they can run more stuff. If you have ever met someone who works at weather simulations, like the ones that predict the weather and tells you that it's going to be sunny in the south of Spain, so thanks, very sunny today. Okay, so those people have PhDs and whatnot, just to say very sunny, but they could use this so the mega clusters arrive to the conclusion that it's going to be sunny much faster. Cool. So now you can know all these things. And you will say, well, but that's kind of cool, but like, I don't really like to look at these plots. Like, I just like to run my weird PyTest modified code that we learned today. That's what I really like. So in Membrane, we have this cool thing now, testing. We have our weird test. Oh, awesome, fantastic. How lovely is this test, huh? You can now, if you install Membrane, it adds a bunch of stuff to your PyTest. So now you can decorate your thing with a decorator. I don't remember even the name decorator of the thing, so I'm going to look at it. Membrane PyTest. So you go to the documentation like a good lad, and wow, Wi-Fi. Okay, so here is a bunch of documentation, but if you check in usage, you can see that you can decorate with this limit memory thing, which I'm going to copy. So if you now go to this test and say PyTest mark limit memory, you can say this test cannot use more than 1 megabyte of memory. So right now, hopefully these numbers are not 1 megabyte of memory, but we will learn very quickly if that is true. PyTest testing. So right now, the test fails because my math is wrong. let's do crazy math here. Okay, this is correct, no? Okay, yes. So now, the test passes, nice. But now you could do something stupid, like for instance, you can say, well, what if we create the letter A a million times? Like that sounds very smart. And now, now you run it and it passes, which is weird. Maybe we need more A's. Uh, Oh, there you go. Too many A's. Oh, kill, too many A's. Like, they're not enough. Did I write it correctly? Oh, there you go. Okay, memory problems. Oh, wow. This is very cool because now the test is passing, right? Like because 1 + 2, even in this universe, is still equal to 3. But because my test is using a lot of memory, in particular more than 1 megabyte, then it's complaining. I can change this unit and I say, well, what about 1 gigabyte? And hopefully this is not more than 1 gigabyte. Okay, and now passes. So this is very cool because that's all. Okay, that's all. It's very cool. Thank you very much. You use memory today.